All right, welcome to part 2 of today's lecture. This is just an example. So we're just going to do more conservation of ideal energy. So this, again, is from another textbook. So what I want you to do is pause the video and think about how would you go through and set up this question. So the first thing I'm going to do is I'm going to draw a picture because one is not given in this particular case. So we're going to have a vertical spring. And it has some spring stiffness constant of 875 newtons per meter. It's attached to a table and it's going to be compressed. Oops. So we're going to compress our spring down. Is this a perfect drawing? No, but it is what it is. So it's going to have a ball on it. Let's give the ball a different color. So it's the ball that we are going to be focusing on when it comes to our conservation of energy, because it's going to be the ball that is compressing the spring down. It is the ball that is going to be launched, and it's the ball that we are looking at the final height for. So, we've compressed the ball. The spring is then going to go back to its original position, and it's going to launch the ball into the air. Pretend that's solid. So we have a couple of different things going for us. We really have 3 different points our ball goes through. We have the ball compressing down. It's then going to, the spring is then going to stretch to equilibrium and then launch the ball. So I'm going to look at 3 different points. 1, 2, 3. I need to establish where I want my y is equal to 0. So in this case, I'm going to want my y to be equal to 0. The same location, I'm going to place my x is equal to 0. And what that just does is it's going to allow me to use x and y the same. So when I compress my spring, I'm decreasing my y value. When my spring is at equilibrium, my y value is at equilibrium. So I'm going to put x is equal to 0 and y is equal to 0 at the same location. And yes, I am using x and y both in the vertical direction. And that is, again, because elastic potential energy uses the equation 1/2 kx squared. In this case, because y is not always going to be equal to x, because when the ball is up in the air, the spring is not coming with it. The spring is just going to equilibrium and launching the ball to height 3. So this is how we are going to be, or I'm going to go through solving this question. So that means that when I go through and set up my table, I look at velocity, x, and y for points 1, 2, 3. So you can kind of set up your table whatever which way you want. So at point 1, I am taking the ball and I'm holding it in position. So that's going to mean that my velocity here is 0. At point 3, this is the highest point, the spring is going to be flying. Or not the spring, the ball is going to be flying. I'm going to call that 0. I don't know what the velocity is at 2, so I'm going to put a question mark there. At point 1, I have compressed my spring 0.16. Technically, I should have a negative sign because I've compressed it, but I am going to be squaring the value. So if you don't include it for x, that's okay because that value gets squared out. At 0, I'm at equilibrium, or sorry, at point 2, I'm at equilibrium. So that's going to be 0. And at point 3, the spring is not stretching. It has launched the ball. So it's not relevant to the ball at point 3 anymore. So it's going to be 0. the spring is no longer relevant to the ball at 0.3, so we don't care about it. If it was attached, that would be a different story, but it tells us the ball is flying above the spring. So we have launched it some height. Now if we look at the height value, the y value, based on where we have set the value equal to 0, I'm going to have negative 0.16. At 0.2, I'm going to have 0. And at 0.3, I don't know what that is. It's something I'm going to have to solve for. So these are the setup for our particular question. So, sorry, I'm just making sure I'm matching the work that I've done on my scratch paper, because otherwise this will get really awkward really fast. So something else we should definitely make sure that we note is that we are going to need mass in this case because we do have elastic potential energy. So that 0.38 kilograms is going to be important. So let's go through and let's try to solve part A. So we are looking at the upward speed when the ball is going to be released. So what that is going to be is we are solving the velocity value at 0.2. And for for point B, we're going to be solving for the how high above the original position is the ball going to fly. Now, if we wanted to make our life a little bit easier for B, we could do that by setting the y is equal to 0 value the same at 0.1. It would work out the same. Again, it's going to determine whether or not we have two terms for position 1 or we have two terms for position 2. So both are valid. It is just a preference as to where you want to put it. I will personally mix mine up, so I'd rather just have both of mine 0 at the same point. But you can change where y is equal to 0. You cannot change where x is equal to 0. So x has to be equal to 0 at 0.2. Y could be equal to 0 at any location you want to put it. But putting it at 0 at either the ball position at 0.1 or 0.2 are the smarter choices that you could use. So let's go ahead and solve part A. So I need to set up my points 1 and 2. So I'm going to have 1/2 mv1 squared plus 1/2 k x1 squared plus plus mg y1. And I'm going to have the same thing, but for 0.2. So now I can go through and I can look at the terms that I've set are equal to 0. So that's going to be my elastic potential energy at 0.2 and my gravitational energy at 0.2. For 0.1, I'm going to be able to get rid of my kinetic energy value. So now I can go through and I can solve for V2. But first, let's just rewrite the equation that we have so we don't accidentally include anything we don't need anymore. So this is the equation that we have. So we're going to need to do a little bit of algebra here. So we're going to have V2 is going to be equal to 2. So we're multiplying everything by 2, dividing by m. So we're going to have k over m x1 squared plus 2 gy1. And we're going to take the square root of that. So again, we can't just explicitly eliminate the mass because mass is not in all three terms. And we can't just explicitly get rid of the 1/2 because 1/2 is not in all three terms. So we need to multiply all terms by 2, divide by m. So we can now plug in our information. So K was given as 857 newtons per meter. The mass of my ball is 0.38, technically 0 kilograms. My position is negative 0.16 meters. That's going to get squared, plus 2 times the acceleration due to gravity here on Earth, times the height of my ball at point 1. Again, because I've said y is equal to 0 at point 2, it's going to be negative 0.16. If I had made y is equal to 0 at the point 1, I would subtract over mgy2, which would be minus 2 times 9.8 times positive 1.6. So mathematically, it ends up being the exact same equation that we have now. It's just how we got there was a little different. And I need to take the square root of all of that. So now we take this and we plug it into a calculator. Be careful that you do not forget this squared here. It is the most common thing I see happen in conservation of energy questions when algebra has occurred, is squares have been getting dropped. So please make sure that you remember the square. It happened a lot on exam 1 where people just drop squares when using the kinematic equations. We want to make sure we're not bringing that habit into the exam, or we don't want to bring that habit moving forward, especially since we're going to be dealing with a lot of squares when dealing with conservation of energy. So assuming I plugged this in correctly, which I'm guessing I did because I got the same answer 3 times, I got 7.4707 meters per second for my launching speed. So that would be 7.47 meters per second because I was given 3 significant figures for this particular question. So in part A here, we have set up the conservation of energy between when the ball is compressed down on the spring to the instant the ball is getting launched. So the ball is at equilibrium position and it is going to start now being launched off of the spring. So because of that, and because of where we set y is equal to 0, we could eliminate a couple of terms. We were able to go through and solve for the speed at point 2. Now we need to look at for B, which is solving for the total height that the spring or that the ball moves above its starting position. So again, because everything is explicitly given for point 1, it's point 1 that I want to use. And I want to compare point 1 to point 3. It's equally valid to use point 2 and point 3, but you just need to remember to carry extra significant digits. Do not use 7.47. You would need to use 7.4707. You need to use those extra digits. So for B here, we're going to set this up. Again, we're going to use half m v1 squared plus 1/2 k x1 squared plus mg y1 and the same equation for 3. So what I can do now is I can get rid of the terms again I don't have. I don't have any kinetic energy at point 1. My ball is at the highest point. It's at its apex in the vertical directions, which means its velocity in y is equal to 0. And I'm not attached to the spring, so I have no elastic potential energy. So by using point 1 and 3, I also now have the ability to say that, well, my change in position that I'm solving for, well, that's y3 minus y1. I can rearrange my equation such that I have it. I have kx1 squared is equal to mg y3 minus y1. This is what I'm solving for. So I'm not going to have to go in and add another 0.16 to my answer for solving the height. It's already going to be included because of how I've arranged my equation. If you use 0.2, you're going to have to add that height of 0.16 in, assuming you use the same y is equal to 0 value. That's kind of the thing about conservation of energy, is there are, again, a lot of ways you can solve these questions, right? We could use 0.1 or 0.2 to solve this one. We could use different locations where y is equal to 0. Setting y is equal to 0 at a location is going to somewhat be a preference. So do you like using zeros together or separate? Do you want to make it easy on yourself or not? Because we could have put y is equal to 0 at the maximum height and just had an energy value equal to 0. It would be valid. Be a little weird, but we could do it. So, we need to go through and just make sure that we are using values that we personally can then do the math with. So we are now going to arrange our equation so that delta y, which is what we're solving for, we have kx1 squared over 2mg. So k is going to be equal to 875 newtons per meter. My initial position that I've compressed is negative 0.16 meters, and that gets squared 2 times the mass, so 0.38 kilograms, times the acceleration due to gravity. So with this, we now can take it and plug it into a calculator. I've run out of space, so I'm going to go to here. I got that delta y was equal to 3.00752 meters. Again, we wanted 3 sig figs in our answer, so 3.01 meters would be our answer. So in solving this question, again, I, in doing my version of the example, have chosen where y was equal to 0, such that x and y were equal to 0 at the same point, and then I based my calculations off of that. I just want to really briefly talk about the other way you could go through and solve this that is equally valid. It's just personally, I know I would screw this one up. That is why I don't use it. If it helps you out, go for it. So again, we're going to have the same starting picture. We've compressed, we're about to get launched, and we have launched. So we're still going to refer to these as the same points. Let me just write that this is a different 0. So, regardless of what I want to say, the velocity values are going to be the same for the 3 points. I'm still going to have 0, some unknown, and 0. Those are going to remain constant. My x value is still going to be negative 0.16 for 1, still going to be 0 for 2, and it's still going to be 0 at 3. Our x value doesn't care. That is set in stone with what it can be. It's the y value that can change. So if we wanted to, we could set y is equal to 0 down here. And what that does is it says that at position 1, my gravitational potential energy is 0. At position 2, my height is positive 0.16, and I still don't know the height in which I am launching. When we compare points 1 and 2, doing the math, it's going to work out to be the exact same value. because of how we then go through and set this up. When we want to look at point 3, we can still compare it to point 1 or point 2, depending on which one we want to use. If we go directly to point 1, then we just solve for the height above y is equal to 0. If we solve for using point 2, we're going to have to go in and add that 0.16 that we are above the starting point. So again, it works out the exact same way. It's just my personal preference is I don't like having different locations for 0. So that is why I used the first method. This second method is valid. The way that you tell me where y is equal to 0 is you draw me a picture, and that way I know what you are doing and I can base what I'm looking at off of your picture. So again, pictures, as always in physics, super important, especially when somebody is going to be looking and grading your particular questions. All right, so that's going to wrap it up for this second video. This is going to be the last of the big examples for today's lecture, but we do have another video where we're going to talk about energy graphs.